Welcome to this lecture on stochastic processes and queuing theory. Today, we are going to explore a fascinating topic called generalized independent Bernoulli trials. If you have ever wondered how to calculate probabilities when the rules of the game keep changing with every step, you are in the right place. We will build this concept from the ground up, so do not worry if it sounds complex right now. Let us dive in and see how this works in the real world. Now that we know our topic, let us understand what it actually means. Imagine you are practicing basketball. If you shoot from the exact same spot every time, your chance of scoring remains constant. That is a standard Bernoulli trial. But what if you move around? Your first shot is a layup, the second is a three-pointer, and the third is from half court. Your chance of making the shot changes every single time. This is exactly what generalized independent Bernoulli trials represent. The trials are still independent, meaning missing one shot does not physically affect the next, but the probability of success is no longer a fixed number. To analyze this changing scenario mathematically, we use a tool called an indicator variable. Think of an indicator variable as a simple mathematical switch. It turns on, meaning it equals 1 if an event happens, and stays off, meaning it equals 0 if it does not. For the ith trial, the probability that the switch turns on is exactly equal to the success probability of that specific trial, which we call pi. As the trial becomes easier, pi increases and the switch is more likely to turn on. Conversely, the probability that the switch stays off is the failure probability, qi. Since there are only two outcomes, success and failure must add up to 100%, making qi exactly 1 minus pi. With our mathematical switches defined, let us look at what happens when we perform a whole sequence of these trials. Suppose we want to find the total number of successes after n trials. We can represent this total, which we call Sn, by simply adding up all of our individual mathematical switches. Because each switch only adds a 1 when a success happens, adding them all together perfectly counts the total successes across the entire sequence. To find the average outcome, if we repeated this sequence millions of times, we use a powerful rule called the linearity of expectation. This rule tells us that the expected value of a sum is always equal to the sum of the individual expected values, even if the probabilities change every time. This brings us to the formula for the expected number of successes. We know that for any indicator variable, its expected value is simply its probability of being 1. Therefore, the expected value of the ith trial is just pi. By substituting these individual probabilities back into our sum equation, we get this highly useful formula. It tells us that to find the average number of successes in a generalized sequence, we simply add up all the individual success probabilities from the first trial to the nth trial. If we increase the probability of success on any single trial, the overall expected number of successes will increase by that exact same amount. Now that we know how to count expected successes, let us explore a major real-world application, reliability engineering. This is the study of how long machines, software, or systems can operate without breaking down. Imagine a machine component that ages over time. The probability that it survives its first month might be high, but as it gets older and wears out, its chance of surviving the second month drops. If we want to know the probability that the machine survives all n months without failing, we must look at the entire sequence of trials. Because the months are independent, we can determine the total reliability of the system. To find that total reliability, we use this multiplication formula. Here, R stands for the total reliability of the system. It shows that the system only survives if it passes trial 1, and trial 2 and trial 3, all the way to trial n. In probability, the word "and" for independent events means we multiply. We are multiplying the individual survival probabilities together. Because every probability is a fraction less than 1, multiplying them together means the overall reliability R will always be smaller than the weakest individual link. If any single component's survival chance decreases, the entire system's reliability drops significantly. Let us see this in action with a concrete example. A factory uses 3 different machines to test a product sequentially. The first machine is brand new with a pass probability of 0.9. The second is older with a probability of 0.8, and the third is very old with a probability of 0.7. First, we are asked to find the expected number of machines the product will pass. We start by writing out the expectation formula for 3 trials, which tells us to sum the 3 individual probabilities. We substitute 0.9, 0.8, and 0.7 into our equation. Adding these gives us 2.4. This means if we tested thousands of products, on average, they would pass 2.4 machines each. Continuing with the same factory setup, we now need to find the probability that the product passes all 3 machines. To find this, we multiply the individual probabilities together, representing the reliability of this series system. We substitute the values 0.9, 0.8, and 0.7 into the multiplication. Calculating this gives us 0.504. The probability of the product passing all 3 machines is 50.4%. This perfectly illustrates our earlier point. Reliability drops when components are placed in a sequence, even if the individual components are relatively strong. To visualize what we just calculated, let us look at this timeline of generalized trials. You are seeing 3 sequential stages, representing our 3 machines. The horizontal arrows show the progression from trial 1 to trial 3. At each node, there is an upward arrow representing the probability of success, Pi, and a downward arrow representing the probability of failure, Qi. Notice how the success probabilities decrease from 0.9 to 0.7 as we move right, while the failure probabilities increase from 0.1 to 0.3. This diagram clearly shows how the rules change at every step, yet the trials remain connected in a sequence. Now that we have visualized the sequence, let us introduce another critical concept, the waiting time distribution. A waiting time distribution is a mathematical formula that tells us the probability of having to wait exactly n trials before we achieve our rth success. In a standard scenario where the probability never changes, this is modeled by the negative binomial distribution. It calculates the chance of getting exactly r-1 successes in the first n-1 trials, and then finally getting the rth success on the very last trial. But when probabilities change at every step, we need a new approach. Before we generalize, let us briefly look at the standard negative binomial formula for context. Here, WR represents the waiting time until the rth success. The combination term counts all the different ways we could arrange the earlier successes. The terms p to the power of r and q to the power of n minus r represent the constant probabilities of those successes and failures. However, when we generalize this to non-identical probabilities, the formula becomes more complex. We can no longer use a simple exponent like p to the power of r, because every single success now has a completely different probability. This leads us to the generalized waiting time formula. Instead of a simple exponent, we must calculate the probability of getting exactly r-1 successes in the first n-1 trials using the specific changing probabilities. We call this intermediate probability P of Sn-1 equals r-1. Then we multiply that result by the probability of success on the specific nth trial, which is Pn. This ensures we account for the exact difficulty of the final winning trial. If the final trial is very difficult, the overall probability of finishing exactly on that step will be significantly lower. Let us apply this new formula to a real scenario. A student is taking a series of increasingly difficult driving tests. The probability of passing the first test is 0.6, the second is 0.5, and the third is 0.4. We need to find the probability that the student achieves exactly their second success on their third attempt. This means the student must get exactly one success in the first two trials and then succeed on the third trial. We will first calculate the chance of getting exactly one success in the first two trials. This formula represents the two possible ways this can happen: passing the first and failing the second, or failing the first and passing the second. Continuing with our calculation, we need to substitute the given values into our intermediate formula. We must remember that the failure probability Qi is always 1 minus Pi. So Q1 is 0.4 and Q2 is 0.5. We substitute 0.6 for P1, 0.5 for Q2, 0.4 for Q1 and 0.5 for P2. Multiplying these pairs gives us 0.30 plus 0.20. Adding them together, we find that the probability of getting exactly one success in the first two trials is 0.50. We are now ready for the final step. Now that we have our intermediate result, we set up the final waiting time formula. We multiply the probability of getting one success in the first two trials by the probability of passing the final third test. We substitute 0.50 for the first part and 0.4 for the third test success probability. Multiplying these gives us 0.20. The final probability is 20%. This means there is exactly a 20% chance that the student will have to wait until the third test to secure their second overall pass. This perfectly demonstrates how we handle waiting times when the difficulty changes at every step. We have covered a lot of ground today, so let us summarize the key takeaways. First, generalized independent Bernoulli trials allow us to model real-world situations where the chance of success changes over time but the events remain completely independent. Second, by assigning a unique probability to each trial, we can accurately calculate expected successes using the sum of probabilities and system reliability using their product. Finally, we learned how to calculate complex waiting times by breaking the sequence into earlier successes and the final winning trial. Understanding this concept bridges the gap between simple coin flips and the unpredictable nature of the real world. You now have the tools to analyze these dynamic probabilities.